Hi there. Here we go with this whole new unit about volume. What is volume? Well, I know that when we're listening to music and a good song comes on, sometimes we might say, hey, turn up the volume. I don't know if anybody actually says that anymore. Maybe it's just turn it up. But when I associated volume, the first thing that came to mind was sound. But this is kind of important that we know what volume is as well. Sometimes in the US customary units, which we kind of talked about in ratios, we call it capacity. Okay. Usually capacity though has to do with liquid measurements. Okay. Like this bottle of water right here has a liquid capacity, but it could still be called volume. All right. The volume of this bottle of water happens to be 1.5 liters. But we're going to talk about solid volume. We're going to talk about three-dimensional shapes. Okay, kind of like this box here, or the one behind me that I so awesomely drew up there. No, I'm not an artist. And we're going to talk about what it means and how do we find out what the volume is. Okay, now volume is basically just an extension of area. I kind of went through this little demonstration previously in the area when we were talking about dimensions, how a dot technically, when we talk about a dot, it doesn't have any dimensions. It doesn't have a length, it doesn't have a width, certainly doesn't have a height, right? But if I were to extend that dot in one direction, it becomes a line. That's a one-dimensional object, okay? It has one dimension. And in this case, I could probably say that it has the dimension of height because it's going up and down. And then if I took this line and I moved the whole line that way, so that it extended out this way, I would have a two-dimensional object. It has two dimensions, and in this case I can see that it's probably height, and I could call this width, okay? Now, if I take that whole face, the whole thing, and extend it out in another direction, 90 degrees to be exact, it becomes a three-dimensional object. Okay, and if I know how to draw, I could show you that it kind of looks like a cube, huh? I could say as long as every one of these dimensions is the same, but now it has three dimensions. It has the up and down dimension. It has this dimension. Both of those I had when I was talking about two-dimensional objects. And now it has this new one going out that way. All right. Kind of like if I were to show you this box, but if I could hold it up so that you could just see this front face right here, you'd say, oh, two-dimensional object. That looks like a rectangle. But what if I held it like this? And you can see all three dimensions. This one, and this one. Okay? Now, what do we call those? Well, this is a tricky one because when I was in math class, I was always told that it was length, width, and height. And usually that made sense. I could say, okay, well this one I'll call the length, and this one I'll call the width, because it's kind of showing how wide it is. And height is easy because that's how tall it is, right? So if I were to hold up my box again, you could see that this could be the width, maybe. This could be the length, and this would be the height. Sometimes that can be a little confusing though. Because what do you call what? All right. And some people are very, very tempted to switch these two around. And this is the width and this is the length. And honestly, guys, it doesn't matter. Let me show you why. Now, when I found the area of just this front face, how would I do that? How do I find the area of a rectangle, just this rectangle? Well, it basically is just saying, okay, well, what's the height? And how many lengths fit in there. So if I were to cut this up, if I were to say that this is 5 units, I'll use U for units. This is 5 units long. This is 3 units long. That's kind of like saying, oh, well, okay, let's cut this length into 5 units. 1, 2, 3, 1, 2, 3, 4, 5. Got 5 units there. See that? And then I take the ruler and I say, okay, well, this is 3 units, 1, 2, 3. Area is just how many square units are in there. So if I were to extend these lines all the way across, I would say, okay, let's count up all the square units. There's 15 in there. I know that because I know that 3 times 5 is 15, but you could actually go through and count those and you would see 15 square units, right? Easy enough. How does that extend to volume? Well, what if I know that this width is also 2 units? Okay? That means if I were to extend these lines all the way across, on top of the shape and on the side of the shape right there, there's actually 2 units cutting this up. So I would have to extend that one all the way up and all the way across. And now I have a whole bunch of cubes all set up in this shape here. And my job is to figure out, well, how many cubes is that? So if you can kind of look at this, I have a front set of cubes where this line cuts it right here. And I have a back set of cubes there as well. So I have 15 up front, I know that because I just counted them, right? There's 15 squares on this face. If I were to make those 3-dimensional, there would still be 15 cubes. But I can't forget about the cubes in the back. There's also 15 of those, right? Because at this kind of shape, it's basically like saying, here's 15 cubes, and then behind that is the same number of cubes. All right? So basically, by looking at this, I can tell that the volume, big V for volume, of this whole shape right here is the length and the width, I'm sorry, the length and the height, length times height, times the width. Put the numbers in there, that's 5 times the 3 times the 2. And if I know there's 15 in front and 15 in the back, that gives me 30. This right here is the front, times 2 also includes the ones in the back. That's 30 units. And they have 3 dimensions this time, okay? The whole reason that we were talking about area having 2 dimensions, and we wouldn't forget to put that in our answer, we can't forget to put the fact that there are 3 dimensions in each one of these cubes either. So we actually put 30 units cubed this time, okay? Because they're not just squares anymore, they're cubes. With me on that? Okay. To give you a couple more names for these pieces. First of all, I'm going to go ahead and write that formula. Volume, I said the length times the height times the width. Let me just leave that there for a minute. Sometimes though, you'll hear some people call this the base. This one right here that we used to call the length, we can also call a base. Why? Well, because that's where the shape is actually sitting on. It's the base of the shape, right? I've never really heard anybody call this anything other than height, so we'll leave that there. And now does this kind of look like a formula we've dealt with before? Do you remember the formula for parallelogram? Base times height. Do you remember the formula for triangle? Half times base times height, or base times height over 2. And then there was also the trapezoid, where we were talking about bases and heights. Okay? Sometimes people will call this the height and the base just to make it a little bit simpler for them to see, and also to make it consistent with those shapes that we've already talked about. So what do they call this? Generally, when you're looking at something like this, you have a base, you have a height, and then you also have how deep it is. So you might see some people call it the depth. It's not wrong. It's just another name for these two things right here that I think actually kind of help out, okay? So volume could be length times height times width, or volume could be height, or well, let's keep it consistent. Base times height times depth. Either way, right? Same thing. Now let's look a little more closely at these two formulas. These two formulas, first of all, they're the same formula, right? They just have different names, will get you the volume of any rectangular prism ever, okay? Any box that has 3 dimensions and is made out of a rectangle with 90-degree angles like this, anything that looks like a box, okay? This is a rectangular prism. This is sort of a rectangular prism. Any box, okay? Your bookshelf, your computer sometimes, if you have a computer tower, any box. This formula will get you the volume, how many cubed units are inside of it. Is it always going to be written like this? What if it was written like this? What if I wanted to take the length times the width times the height? Give you the same thing? Think about your properties of multiplication, the associative and the commutative, okay? It doesn't matter which order you multiplied these in, and it doesn't matter which order you write them in. You're always going to get the same result, right? Because of the associative and commutative properties of multiplication. You knew those would come in handy, right? Same with this one. If I wanted to write this one as base times depth times height, same result, totally going to be the same, okay? It doesn't matter which order you write these in. You're always going to get the same result thanks to that commutative and associative properties of multiplication. Now, I don't actually have an exercise sheet for you that I've made. What I have is a whole ton of practice finding the area and the base. Finding the area of the base sometimes, and generally finding the volume of different kinds of rectangular prisms. I'm not going to have an exercise review video, but I did make you an exercise answer key at the end, so that should help. Let me give you one more thing that you're going to see though before you get started, just so you don't get confused or stuck. Let's say that I have a height of a rectangular prism of, let's make this 4. Okay, I'll make this 4 also, and this one over here is 2. Let's also call this height, we'll call this base, and we'll call this depth. Every once in a while, you're not actually going to see these two measurements. You're actually going to see something that somebody said, hey look, here is the base. In other words, they're going to give you the area of the floor, the base of this shape. So they may already do this for you, okay? They may say the base, and they'll use a big B, is 8. I said 8 because it was 4 times 2. That gives me the area of just the floor. And notice I had big B base. So now I'm asking you, what's the volume of this rectangular prism right here? Okay? And in this case, since I've already multiplied these two together, the volume is going to be big B base times height. This right here, guys, is a very important formula in geometry, and you'll see that as we go into 7th and 8th grade, also when we deal with cylinders and even cones and pyramids and stuff like that. Base, big base, the area of the floor times its height is a very important volume formula. Now, don't get ahead of ourselves too much, okay? I just want to make sure that you recognize that if they give you a big B base and a height, just multiply those two together and you have got your answer in units cubed. Don't forget the cubed, okay? Because all we're doing is figuring out how many cubes are inside of that shape. Think you got it? Go ahead and give those ones a shot, and then we're going to go into something kind of interesting, and that'll be in the next lesson. So good luck with those exercises, and I'll see you in the next lesson.